Welcome everyone to the One World Combinatorics on Words seminar. Our speaker today is Štěpán Starosta from the Czech Technical University in Prague, and he is going to speak to us about faithful representations of the Sturmian monoid.
Okay, thank you for the introduction, and thank you for the opportunity to speak at the seminar. The title of the talk is on faithful representation of Sturmian monoid, and it's exactly what I'm going to speak about. And this is a joint work with Jana Lepšová and Edita Pelantová. Okay, so I'll start with what a faithful representation is. So I have some monoid. It's here, it's M, and the operation is star. Okay, and I have some vector space and a set of all linear operators over a vector space. It can be any vector space, and the representation of the monoid M is a mapping from the monoid to the set of these linear operators, so L of V. And the mapping needs to preserve the operation. Okay, so it's a morphism. So if I map a composition of two elements of the monoid, I can do the composition later in the set of linear operators. Here with the this is the generic composition of mappings. So in the context of combinatorics on words, there's an example of a representation that we all know. First, let A be a finite alphabet, and if I take the monoid of all morphisms over this finite alphabet with the usual composition of mappings, then if I associate to each morphism its incidence matrix, so I have a morphism phi, and I have the incidence matrix M phi, then this is a representation. Here, I'm identifying already the linear operator with its matrix, since I'm in the, well, at least for me, nice case when the dimension of the vector space is finite. So this is going to be the idea also in what's going to follow. We will have a finite space, and we will be working with matrices. Okay, so here, this is matrix multiplication. Okay. So that's a representation, and we say, oh, now it's going to disappear. Yeah, the representation is faithful if this mapping from my monoid to the set of linear operators is injective. So faithful would be just this one, just saying that my mapping is injective. So, well, if I take a look back on the example, mostly if I take just all the morphisms over, say, at least binary alphabet, I'm going to get a non-injective mapping. So this representation in general is not faithful. I mean the representation by incidence matrices. Okay, so that's faithful representation. And what I'm going to show is how we define the faithful representation of the Sturmian monoid. So just recall what's a Sturmian monoid. Sometimes it's also called monoid of Sturm, and it's the monoid of all Sturmian morphisms. So I will recall what a Sturmian morphism is. So the alphabet is fixed to be binary 0, 1, and a morphism is Sturmian if the image by it of a Sturmian sequence U is again a Sturmian sequence. So this This would be a Sturmian morphism, and actually we can replace the condition here so that it maps only just one sequence that would be called locally Sturmian morphism, but this is equivalent to being Sturmian. So a Sturmian morphism is preserving the property of being a Sturmian sequence. Now this well known how to construct these morphisms. They form a monoid, and we know their generators. So I'm using one of the usual notations for the generators. E, that would stand for the exchange morphism. So this is just exchanging zeros and ones and preserving the lengths. G would be this morphism, okay, and I believe this stands for gauche, so left. And the last one, which is needed to generate the set of all Sturmian morphisms, is G tilde, which is G with the images of letters reversed. Okay. So it's a finitely generated monoid, and I will need a subset of it, which is called special monoid of Sturm or special Sturmian monoid, and this is produced by, say, forgetting about the exchange morphism, and then I need to add some other morphisms that that are, say, friends with G, and that's basically D, which is which stands for droite, so right, and the mirror image of D. And also they were previously there, because if I lose E, I have this relation D equals E composed with G composed with E, so D was definitely in the whole set of morphisms. And so the reason why I focus on this subset will be explained. I will explain it later. It will make some things easier. Okay. So I'll keep this notation. So from now on, my monoid is special Sturmian monoid, and it's this calligraphic M. Okay. So recall now one of the possible definitions of Sturmian sequences using mechanical sequences. So a lower mechanical sequence with the parameter alpha and delta is defined by this difference of rounded values of a multiple of alpha plus delta, and here I don't have this this plus one, and this would be lower mechanical sequence, and the upper mechanical sequence is analogous. I just use the ceiling functions instead of the floor functions in the rounding. And well, it is well known that if I take alpha irrational from between 0 and 1, I obtain a Sturmian sequence, and I'm going to distinguish between taking lower and upper mechanical sequences. So if I take irrational alpha, S alpha delta is going to be the lower Sturmian sequence, and the first parameter alpha is the slope, and the second is usually called the intercept, so delta is intercept. And analogously, if I take the upper Sturmian, upper mechanical sequence. As the definition, I'm going to call these words upper Sturmian sequences, and the notation, the usual notation that you can find, for instance, in Lothair's book is S prime sub alpha delta. Okay. So there's another useful definition, say, well, the definition with mechanical sequences is also related to some geometric concept, but I'm going to recall a slightly different definition using two interval exchanges. Two interval exchange is a mapping from an interval. So here, that would be this upper line. Here I have the basic interval to be left closed, and it's 0 until L0 plus L1, L0 plus L1, and L0 is the length of the first subinterval I sub 0, and L1 is the length of the second subinterval I1, and they are both left closed, right open, and the mapping defined on this is exchanging the two intervals. So it's a piecewise continuous map. If I take an element in the first subinterval, it's going to be mapped or shifted on the end of the whole interval. And if I take x in the other interval, it's going to be shifted here to the left. So the mapping is really exchanging the two intervals, of course, keeping them left closed and right open. So that's exchange of two intervals. And relation with Sturmian sequences is that if I take any point, if I take any point here on the interval, here now it's rho, I apply the mapping T to rho over and over again, and each time I denote into which subinterval I fall. So if I fall into I0, I'm going to write down 0. If I fall into I1, I'm going to write 1. And doing so, I'm going to obtain coding of trajectory of rho with respect to the mapping T, and this coding is going to be Sturmian sequence with the slope that can be calculated from the length of the intervals. So L1 over the length of the large interval, so L0 plus L1, and the intercept can be derived from rho, but I have to again normalize it by the length of the interval. What I'm missing on the slide here is that the slope needs to be irrational. Okay, so the lengths are set that the slope is irrational. So this is not in Q to get a proper Sturmian sequence. And well, when I have a slope and the intercept, I can use a notation on the previous slide, and there's no prime here. I have lower Sturmian sequence, and this is due to taking left closed and right open intervals. So often this picture is done with L0 plus L1 equal to 1. So there's some kind of normalization because those denominators go away. But this is exactly what I want not to do. That's what's going to get me the representation, like not doing the usual normalization of the parameters of a Sturmian word, but just keeping them as I have them here in the picture, well, not normalized. So let's look. Okay. So here's the picture for lower Sturmian sequence. It would be analogous if I want the upper Sturmian sequence. I would have to take right closed, left open intervals, meaning the whole interval and the two subintervals. Okay. So if I don't do the normalization, then a Sturmian sequence U, okay, so U is a Sturmian sequence, is fully described by the setting I had before, by the two lengths of the two subintervals and the intercept, well, or it's the starting point of the trajectory of rho, except for the fact whether it's a lower or upper Sturmian sequence. So except the usual problematic thing of whether we should take left closed or right closed intervals. But besides that, the Sturmian word is described by this triplet. Okay. I can scale the image. So if it's described by one triplet, I can take any positive C and multiply each element of it, and it's going to be a description of the word U also. Okay, that's so in fact, I could have now switched to working with the projective space with rays, say positive rays, but I'll not need this. So I'm going just to stick with these triplets and keeping in mind that multiples describe the same word, except for maybe its lower or upper Sturmian sequence. Okay, so in other words, if I take an upper Sturmian sequence, sorry, a lower Sturmian sequence and an upper Sturmian sequence with the same parameters, alpha and rho, with the same slope and intercept, I'll have the same parameters, meaning the vector of parameters, the two lengths and the intercept, except for some extremal case where the intercept is 0, which is allowed. Then there's this needs to be dealt with by these two cases here. Okay. So now I'll get back to question, and it would be description, or well, finding the representation of special Sturmian monoids, and for that I need to understand how what's happening when I apply one of the generators of special Sturmian monoid. So this can be seen on a picture. It's and just to get an idea what's happening. So I want to apply the morphism G. So it's recalled here, the title, on a Sturmian sequence U. Okay, so it's again it's a Sturmian sequence, and it can be seen on the two interval exchange transformation. So if I look at this upper half, let's say that U has parameters of this interval. That would be L0, L1, and I don't have the other interval, the other parameter, so it can be rho. And the coding of the trajectory is U. And now to find out what's the two interval exchange that is coding G of U, can take a look at G, and so each time I write 0, that would be each time I fall here in the first subinterval, I want to write 0 in G of U. So the lower picture is going to be the two interval exchange transformation that's coding G of U. So each time I'm 0 here, I have a point here which is in the first subinterval I prime sub 0, and I will write 0. Now, if I am in the second subinterval in U, and I write 1, I want that in G of U I have 0 and 1. Okay, so again, I can look here to get this point. So sorry, this is L0, and I fall right in the interval I prime 0, so I'm going to write 0, but then I will move by T prime, the new mapping, to this edit part, and where I'm going to write 1. So the next letter after the 0, which was previously in I1, is going to be 1. Yeah, so this position here, which was not in the previous pictures, that would be exactly, I mean, this position in the images of 1 between the 0 and 1, which are not in this picture. We have no G here. Okay, so I went a bit quickly over this, since I'm going to show how this ends. It's a known result. This is nothing new, and there are many. There are other ways how to see this. If you start with the lower picture, I mean, to get the upper picture, that would be doing Rosy induction on I1 prime. It's the same. Okay. So the reason to show this is just to give some intuition where the next formulas come from. When I apply G to U, I can now, from the lower picture, read the parameters, well, the triplet of parameters of the Sturmian word G of U. So what are the formulas? So it's sorry, lost my, okay. It's a result of Parve from 97. When I apply G to the lower Sturmian word of alpha and of slope alpha and intercept delta, I have the new slope and the new intercept. The mirrored version of G also have the new slope and new intercept, and to get everything I need E. It would be another set of generators of the whole Sturmian monoid. So that's a formula for this. And here there are the denominators that would be the normalization I don't want to do. Okay. So if I lose the normalization and if I want these formulas to correspond exactly what was on the previous slide, I obtain this. Okay. So G of U, that's what we've seen, has parameters. The first interval is the sum of the two, was exactly on the previous slide. Then the new interval for 1, that's of length L1, and with probably some a bit of thought, rho remains fixed. Okay, it's not. I didn't need to move the initial point. Also in my explanation. So this is provided on the fact that the parameters of the Sturmian sequence are L0, L1 row. We can do the same for the remaining, so G tilde D and D tilde. And here, I still don't know whether the Sturmian sequence is lower and upper, and I don't care. It can be both. I'm interested in what's the action of G here. So if I don't do the normalization, what I obtain is nice because it's linear. Okay. No denominators here, and that was the goal. So I can find the matrices of this linear mapping. So R of G is going to have this matrix here. So adding the two first parameters here, keeping the second, and keeping all the slope. And the same goes for the other three generators. So I have 4 matrices, and they were constructed so that if I take a vector of parameters, which are parameters of U, then if I multiply them by one of the 4 matrices here, I obtain parameters of the respective image of the word. So psi here is one of the 4 generators. Okay. Now I need to extend this to the whole special Sturmian monoid, and for that I need to check that there's not going to be a problem. And luckily, we know the presentation of the special Sturmian monoid. So all the relations between the generators, okay, so G tilde, D, that's an ugly M. Okay. All the relations between the generators are generated by these two equalities for and they hold for any case, so there's an infinite number of them. And it's straightforward to check that these are going to be preserved if I extend the definition of a mapping from M to any morphism generated, to any morphism from the special Sturmian monoid. Okay, so I write down psi as a composition of generators, and the assigned matrix is going to be the multiplication of the matrices from the previous slide, okay, based on the decomposition into generators. And we can check by a computation that the previous 4 matrices satisfy the 2 equalities from the presentation. So the definition of here calligraphic R, which is going to be the representation of special Sturmian monoid, is indeed correct. Okay, so we can just extend it very naturally to any morphism from the special Sturmian monoid. Now, one of the reasons to focus just on the special Sturmian monoid is that if I take a morphism from it, it maps a lower Sturmian sequence to a lower Sturmian sequence. Okay, so lower to lower, and upper to upper. Okay. So using this, we can come to the conclusion that the way it is defined on special Sturmian monoid, the map which assigns to every element a 3x3 matrix, is indeed injective. So R, as defined here, is a faithful representation of the special Sturmian monoid M. So here at this point, we could. Okay, I have the slides later, so I'll do the comment. I do the comment later because I have it on the next slide. So let's wait a bit. So just looking at the four matrices, well, let's say the generators of the representation, we can conclude that there's going to be always zeros here on the right. There are two zeros on the first two rows. On the right, there will always be a 1 in the lower right corner, and the way it was constructed is that we are going to retrieve in the upper left corner a 2x2 matrix, which is actually the incidence matrix of the morphism. So I denoted this M sub psi here, so that's the incidence matrix. So that can be seen as an extension of the representation by incidence matrices by adding one more parameter, which is coding the action on the slope, okay? Not just the action on the two intervals, but also on the slope. Okay, and what we can obtain in this moment is that if psi is a primitive morphism from the special Sturmian monoid M, and U is a Sturmian sequence with vector parameters L0, L1, and rho, then the sequence U is fixed by psi if and only if the vector of parameters, well, taken as a column, is an eigenvector of the matrix associated to psi, to the morphism, and moreover, it's an eigenvector associated with the dominant eigenvalue of this matrix. Here, the dominant eigenvalue would be the dominant eigenvalue also of the of the incidence matrix. It's a primitive matrix, so there's a dominant eigenvalue, and because of the two zeros, it's going to be also dominant eigenvalue of the whole matrix, and so this well, this is of course the conclusion of the Perron-Frobenius theorem applied to the incidence matrix. So there are two eigenvalues coming from there, and the third eigenvalue is associated with eigenvector 0, 0, 1. Oh, that's a 1 here. So okay, so we have a strong link with the representation and the fact that U is fixed by a primitive morphism. Okay, I probably need to go a bit faster. So the remark I started previous is that here we could have chosen to work with the whole Sturmian monoid, since if we well, find the matrix of the exchange morphism E in the same way it was done for all the other morphisms, it's going to end up like this, but there's this -1 here. and it would also work, but some things would get more complicated. There would probably need to be case analysis on some places, and since we know that if psi is a Sturmian morphism, then the square is always a special Sturmian monoid. Sorry, it's from the special Sturmian monoid. We can use this and cover well, every possibility on in the case where psi is also fixing a word, because psi squared is going to fix 2, of course. So that's the reason to limit ourselves to this monoid, to have some simpler form of the results. Okay. So before showing some applications of this faithful representation, I'm going to show a characterization of the range. So R of M is the special Sturmian monoid. And so first, the range is a subset of matrices which are 3 by 3 and have determinant 0. So the special linear group. And since we know the form of the matrix is a 2 zeros, it's easy to see that the determinant is going to stay 1. And what we show is that there are 3 convex cones, C1, C2, and C3, which can be used to characterize R of M. So convex cone is a convex set such that C intersection with minus C is only 0, and it needs to be convex. I'll not go through the formulas here, just the result that the range is actually equal to all the matrices of determinant 0, such that they preserve the 3 cones, with the exception that the second cone is preserved by the inverse of the matrix. So that's that would be the sort of the identification of the range of the representation. So we have the representation as the mapping is an isomorphism between M and well, R of M, that's trivial, but we have its characterization by these 3 cones. So I'll be using one of those in a proof. I'll recall it. Okay, that's the end of the first part, and now I'd like to show some applications which well, we managed to give alternative proofs of 3 results and a new one. So let's start with the first application, and it's a proof of one implication in famous Yasutomi's theorem, which is characterizing slope and intercept of a Sturmian sequence, which is fixed by a primitive morphism. Okay, so the characterization of the phenomena when a Sturmian sequence is fixed by a primitive morphism, and it's in terms of, well, the slope and the intercept. And well, it says that they need to belong to the same quadratic field. The algebraic conjugate in this field of the slope needs to be outside of the interval 0, 1, and there's this, well, set of 2 inequalities, third condition. And we managed to give a short proof of the implication when we assume that U is fixed by a morphism, like to obtain this algebraic characterization of slope and intercept. Okay, so I will give a proof of this because it's not really long, using okay, just give a proof. So I'm assuming that U is a Sturmian sequence with parameters 1 minus alpha, alpha and rho. So there's some there is a normalization on the first two parameters. Okay, you can choose this from the multiples. Alpha is from the interval 0, 1, the open interval, irrational, and rho is from the left closed and right open interval 0, 1. And psi is the fixing morphism of U, and it's primitive. And by a theorem that I've shown before, since psi is fixing the morphism, there's a dominant eigenvalue lambda of the matrix representing. So this should be the other psi. I'm not going to fix it probably. Okay. Okay, it's the same psi. And well, I know that there are the 2 zeros in the matrix and the 1 here. So as I've indicated, how this theorem is proven, the lambda is also eigenvalue of the primitive incidence matrix of the morphism. That's the upper left corner of the representation, and we can easily identify its eigenvector. That's going to be 1 minus alpha and alpha. So from this, it follows that lambda is quadratic, irrational, and that the components of the eigenvector belong to the same field. It would be the first 2 points here, and just from the form of the matrix and the fact that lambda is an eigenvalue, I get from the multiplication of the last line an equality which implies that also the third component of P, which is rho, is belongs to the same field. Okay, so I maybe was a bit too quick here. I know that lambda is an eigenvalue associated to the eigenvector P. Okay, so this would be just the multiplication to obtain the last element of lambda times P. Okay, so this is the right side. So items 2 and 3, that's the first part of Yasutomi's characterization, and we need to get the inequalities. It's a bit more work. So the other eigenvalue of so here that's of the representation is the algebraic conjugate of lambda, so lambda bar, and its eigenvector is with the components where I also add bars over the the components. So I denoted P bar, and the last eigenvector, which I already mentioned, is the one with 2 zeros and 1. So I know all the eigenvectors of R of psi, sorry, of R of psi, and from the characterization of the range, that's theorem 2, okay, saying that R of the whole monoid is equal to something. I pick one of the 3 conditions, the one in the middle, saying that R of psi, well, the inverse of R of psi preserves the second cone C2. And by Brouwer's theorem, we conclude, since the cone is fixed by a matrix, that at least one eigenvector of the fixing matrix, so it would be the inverse here, is in the cone, so belongs to C2. I don't like this -1 here, but I'm interested in eigenvectors, and they are the same for the R of psi. So it holds for R of psi also. The matrix is regular. I forgot something. Okay. Yes. So one of the 3 eigenvectors, well, more or less, is going to belong to C2. Okay. So here I just recall what C2 is. I'm going to need it now. So it will be this formula, and it's easy to check. It's not the third one, the one with the 2 zeros. Okay. It's where is it going to fail? The last condition. Okay, well, I'm going to get some nonsense here. It's not going to be P, so the first eigenvector, 1 minus alpha alpha rho, because alpha is in the interval 0, 1, the open interval. So I think that's the second condition. Here, 0 would need to be greater than alpha, which is from 0, 1. So this is not the eigenvector which is in C2. So the last eigenvector, which is p bar, so I lost the bar here. Okay. P bar is in C2, and well, C2 is a cone, so that's like a half of the space. So I need to consider that either P or minus P is in C2, because by picking P, I chose well, one of the eigenvectors of the whole space which is generated. So I need to consider 2 cases here, and just looking at the 2 cases and the fact that it's in C2 from the definition, we can show the rest of Yasutomi's characterization. That would be these 2 conditions. Yeah, so I don't have it here. It's just you need to do the 2 cases and look at these inequalities, and it's going to end up as we want it. Okay, so I was much slower than I hoped to be, so I'll probably go very quickly by over the other 2 applications. So the second application is on a question of Michel decking on the case where I have what slopes and intercepts allow that the upper and lower Sturmian word with the same parameters, with the same slope and intercept are the same, and both are fixed by a primitive morphism, not necessarily the same. So we managed to give another proof of this. That would be, well, the solution to the previous question. So just go over it. We also managed to use the representation to get a result on the number of conjugate morphisms to a fixed Sturmian morphism. So it's known one needs to sum up all the elements in the instant matrix and subtract 1. So we managed to well, give an alternative proof of this. And well, sorry so for going that quickly. I want to spend a bit more time on the last application where we got a new result, and the new result is concerned with what was defined by Sari in 2010 as well, which comes from a result of Sari of 2012, which says that every Sturmian sequence you need 6 factors to write it as a concatenation of squares, and the root of the square is going to be one of these 6 factors. Okay, so I have only 6 possibilities to choose the index I here, and the Sturmian word is going to be concatenated from these squares, which led to a definition by Beltomaki and Whiteland of a square root of a Sturmian word by dropping the exponents, the 2's here. Okay, and they managed to show that the square root here is actually Sturmian, and it preserves the slope, and well, the intercept changes. Okay, so there's some the formula for the intercept, and example, probably skip it. What we've shown is that if a Sturmian sequence is fixed by a primitive morphism, then the square root of the Sturmian morphism, of the Sturmian sequence is fixed by some other morphism, which is necessarily a conjugate of one of the powers of the original fixing morphism, and we need to consider up to the 4th power. Okay, so it's k is bounded by 4. So yeah, we can of course we can take 4 here to be the, if you want to choose one, it's going to work. So I have an example. I'm running out of time, so I'll skip it again. And with an obvious open question, and that would be facial representation of some other class of morphisms. So now we are looking at well, the famous geometric representation of Arnoux and Rosé of Arnoux-Rosé sequences. So because the original point when we saw the linear mapping was from the 2 interval exchange transformation. So we hope to be able to identify the right parameters here also to obtain a representation. It needs to be linear. Okay, that's it. Thank you for your attention.
Oh, thank you very much, Štěpán. Does anyone have any questions?
Could I have a question?
Oh, yes, please.
So in the last of your talk, there is a square root of Sturmian words.
Yes.
So my question is that is there any other class which, so we can take a square root?
You mean a class of words?
Yes, we can take a square root. So
I'm not aware. This is purely based on the result of Sari, which is quite special for Sturmian words. So I'm not aware if there's any large class that would have this property of being able to write as a concatenation of a finite number of words and their squares actually. So I don't know if there's some class that can do it. Don't think so.
Thank you. Okay.
Christoph, you had a question?
Yes, thank you for the nice talk and the nice results. I like
Thank you.
this faithful representation. And actually, what I can ask, I already had an mail exchange with Štěpán, so I wondered if their representations of the special Sturmian monoid extends to the whole group of automorphism of F2, the free group on two generators. Perhaps not the whole automorphism group, but just the one that have determinant one. It's like the special one. And so I think since we know, perhaps Stepan, you have already done that. We know there is a known presentation of this group by Nielsen, I suppose, and so you just have to verify if your matrices verify the presentations, I suppose.
Yes, exactly. I think it's going to work, but I haven't checked it yet. But it's a very nice question. Thank you.
But it could be not faithful. This is not evident at all that it will be faithful.
That's not evident. That's true.
Mm-hmm.
Okay, so maybe it can be like improved by adding another parameter, making the matrices 4x4, and then obtain the injectivity.
Yes. Mm-hmm. Anyway, thank you very much.
Thank you. Are there any other questions? If not, thank you all for coming to the seminar today.